Okay, chapter 16, part 4. Let's finish up Diels Alder. So we've discussed the mechanism, we've discussed stereochemistry, we've looked at alkynes as dienophiles, and we've talked about the diene and its need to be in the S-cis conformation, and what to do if you form a bicyclic compound. So next, we are going to talk about regioselectivity. Now, there are a few different items in here that you could get into, but we're going to focus just on one. And that's when we have an asymmetrical diene, like the one in the picture here, and an asymmetric dienophile. As long as there's symmetry in one of them, then there's only one way you can make the product. All right, it doesn't matter if this is flipped over. It doesn't matter if the OME was here. You're going to make the same product regardless. But when we have an asymmetric diene and dienophile, there are two different options. There's the 1,4 and the 1,3 option. The 1,4 is the major product. What can be tricky is there's no particular reason that this has to be drawn this way. I could also draw it this way, right? That's the same molecule. So it's your job to figure out, are they going to react the way they're drawn, or are we going to flip them around? In this scenario, if I want to draw the major product, then I need to draw it a little bit different, right? You could either do your arrows crossing, or you could flip it around. But what's important here is that we wind up with that 1,4 separation between the two groups on our asymmetric starting materials. Right? So this is just one more detail that you need to know to predict the proper major products. There's a little bit of background on why this happens. It has to do with the resonance and where the electron density is really located. And when we have something that's electron donating on our diene, it puts even more electron density around one of those outer carbons. And then our dienophile is pulling electron density away. But if you look at the resonance, the positive charge actually winds up on the carbon that's further away from it. So the most likely scenario is the electron-rich carbon here is going to be attracted to that electron-poor carbon in the dienophile. I will not ask you to draw, or I will not ask you about the resonance structures, but that is a little bit of explanation as to why this occurs. And so you can see now, if we flip this over, it is still just the same mechanism. Now, before we move on, let's try a couple of practice problems that you might encounter. So let's say that we're dealing with, and I'm just going to turn it on its head a little bit here. And why don't we do, you could even extrapolate this out to alkynes. Let's put a C in there. Now, I don't have it set up so that it's obvious how the Diels Alder will work. This is because I want us to think. We're going to have to spin this one around, so that's fairly easy to start off with. All right, I'm gonna turn it on its side because that's what I'm used to seeing. The OH depending on if I flipped it up or down, could be up here or over here. It doesn't really matter. Now, I see that I have an asymmetric alkyne. I know that if I have two asymmetric starting materials, I want them to be further apart. So I'm going to put the CN on the bottom. I can practice with my mechanism. And now I'm going to go ahead and predict that product. I'm going to have two double bonds because I had an alkyne. And I'm going to have that 1,4 separation. Another kind of problem that I really like and that there is more practice with in the old homework assignment and maybe on the practice exam, if you're looking for more retro Diels Alder problems, ask me because I definitely have some extras I can push out for you. But just to get us started, let's say we were looking at something like this. And let's not even worry about it being asymmetric. Here we go. Okay, if I asked you to go backwards, what are the retro Diels Alder products? Or what would the starting materials be to make this? Well, I see it's a 6-membered ring, and since it has two double bonds, I know that one of them was an alkyne. And I did that on purpose so that you had to think a little bit harder. Which one of these double bonds was most likely to come from the dienophile? Now, I'm going to do this wrong first, because why not? I want to show you. If I try to cut it here, and I say that these two carbons were part of the dienophile, well, it's attached to methyl groups. Those are not electron withdrawing. That would not be a good dienophile. But what about if I cut it here? Now, my two carbons from my alkyne have a carboxylic acid attached. That makes a lot more sense. So what that would leave us with would be 1, 2, 3, 4. And you can choose to draw that how you'd like, but that's what your diene would be. And then these two carbons, this would be your dienophile with your carboxylic acid attached. All right, so make sure that you do a handful of Diels Alder problems going forward, going backwards, that practice with regio and stereochemistry. I think that you'll find after some practice you will get those down pretty quickly. All right, now the last thing that we'll want to talk about has to do with our frontier orbitals. So we're going to look at some frontier chemistry. One of the reasons that this works so well has to do with the electrons in your diene, right? When we think about our diene, we think about those electrons being attracted to our dienophile that has an electron withdrawing group. So we're thinking about these high energy electrons being attracted to the dienophile. And where are they going to be attracted to? They're going to go to the lowest unoccupied molecular orbital. So we're focused on this molecular orbital interacting with this molecular orbital. Now, look at the colors. This is going to be interesting. This is why this works. When they come together, okay, so several slides to say what I just said, right? As they come together, look at what we have. You've got your overlap over here that puts blue on the outside. In the back, the overlap is flipped, so you have red on the outside. The LUMO of the dienophile has the node in it, so blue is able to line up with red. This is called symmetry allowed, right? So when we think about the Diels Alder reaction, the 4+2 cycloaddition, the reason they work so well is because they are symmetry allowed. We have conservation of orbital symmetry. We are able to form constructive overlap the sigma bonds form easily. Now, why don't we see the same thing happen with the 2+2 cycloaddition? In theory, ethylene could react with itself and form cyclobutane, but it doesn't happen. When you put ethylene together, no cyclobutane is made. However, if you shine the right light on it, it does work. So we're going to explore how molecular orbital theory can help us to understand that. If we're looking at two molecules of ethylene, they each only have one double bond. So we have, let's see, if we're going to have two of these, right, where the HOMO of one is everything is constructive. The LUMO, they're out of phase. You have a node. So when you try to get a reaction between the HOMO of one ethylene and the LUMO of another, the blue and the blue aren't necessarily going to match up. The red and the red aren't going to match up. One side will match, the other side will not, and you don't get a bond formed. This is called symmetry forbidden. However, if you shine the right wavelength of light, unless there is light, then this reaction suddenly works. Now, why is that? What happens when we shine a certain wavelength of light onto this sample of ethylene? Well, one of the electrons absorbs however much energy this is and moves into the higher energy orbital. And now you have an excited state that has a different HOMO, highest occupied molecular orbital, and a ground state that has the same scenario, but that's LUMO. And so the excited one can react with the LUMO of the ground state, so that you have one excited ethylene reacting with one ground state ethylene, and suddenly now it's symmetry allowed. Okay, I don't know. I'm a little punchy. Here we go. And so this explains this photochemical reaction, right? This is a reaction that only goes forward if we add the right wavelength of light, the right energy photons. I only left these slides in here because I think they're interesting. I'm not going to ask you any questions, but there are a couple little pages towards the end of chapter 16 if you skip past the other pericyclic reactions, and you get a little bit of information about the chemistry of color. High conjugation usually leads to interesting colors, and so that's why this fits in this part of this chapter. And there is that then flows into the chemistry of vision. And so it's an interesting section. If that's something that interests you, it's at the end of chapter 16.